But today we have from the Department of Biology, Jordan Marshall, who will be talking about forest change over time using stages to interpret the past and the future. Jordan.
Thank you. So most of my research is in forests, but I do research in sand dunes as well. And one of the forests that we'll talk about today interacts with sand dunes, and there's kind of an overlap there. But I like to think about forests as time machines that only move in one direction, but we can look back at what they did in the past to get an idea of where they are now and where they're going to go in the future. So mainly just doing surveys and trying to understand what's happening in the forest and where that's going to go in the future. So the first thing we have to talk about is what is a forest? So usually we think about forests as just being a group of trees, but in reality it's a three-dimensional ecosystem that has lots of layers that build up. So we get the understory, and we get mid-story, and we get the overstory, and we get dead things in there, and there's some deer in the background, and we get all of these things interacting together. So that's what makes it an ecosystem that covers three-dimensional space. But we also have to think about that fourth dimension of time, because forests are never stagnant. They're always moving forward. They're always changing through time. So our forests are dominated by trees. They're the defining characteristic that basically defines that three-dimensional space. But then we have to always include the animals and the fungi and the bacteria and anything that's alive and anything that's dead, and the abiotic stuff. So the minerals in the soil and the water moving through and the weather patterns and the climate of that region all interact together to define that forest. And again, they change through time. They're never stagnant. They're always moving forward. So they're like every time machine that exists, in that they move forward in time. One day at a time, they move through that temporal space. As it changes, individual trees are lost. They fall down. They become coarse, woody debris. New ones come in and regenerate from seed. Whole species are lost from the forest and new ones come in. And so there's always this kind of structural change, so trees falling down, and compositional change with changes in species and the dominant individuals. And then disturbance also happens over time. And disturbance is a discrete event that happens in time and space. So there's a discrete boundary in time. So there's a time before the disturbance, there's a time after it. There's a discrete boundary in space. So there's inside the disturbance and outside the disturbance. And we usually use fire as kind of this classical kind of explanation of disturbance, where there's a boundary to a fire. There's an inside the fire and an outside the fire. There's a before the fire and after the fire. So there's this discrete kind of boundaries around disturbances, and those change over time. What's there, what's actually defining the forest changes over time. And then us as humans, we create disturbances as well by cutting down trees. We harvest trees, we introduce new species, so we change the composition over time by introducing new things to the forest. So we're involved as humans, and there's very few forests that aren't impacted by humans anymore. And the reason forests are important is because they provide ecosystem services. They provide us with services that we could never replicate, or it would be cost prohibitive to actually do those things ourselves. So carbon sequestration is a major ecosystem service for forests, in that as the trees photosynthesize and they're taking carbon dioxide out of the atmosphere, they lock that carbon away in the wood. And so a tree that's 80 years old has carbon that they've sequestered for all those decades and are holding that into storage. And then when a tree does die and it starts to decompose, that carbon gets released and gets reincorporated and recycled back into the environment. And so we have nutrient cycling that occurs. Nitrogen, phosphorus, potassium all cycle through the ecosystem. And then water filtering is another really important ecosystem service, where because we have all these plants, trees and the understory plants, water can percolate down into the soil, and as it moves vertically down and then horizontally through the soil, there's filtration that happens. And if we tried to filter water at the rate and at the quality that forests do it, it would be extremely expensive and we would never be able to actually do it. So forests are really important for our own health, but also the health of the planet. So most of my research is in the Great Lakes region. specifically the lower Great Lakes. So I've done work in Indiana, Michigan, and Ohio for much of my academic career, but I've done some stuff in Wisconsin and Minnesota and up through the Great Lakes in Pennsylvania and New York. But for this talk, we're going to focus on these 3 states because that's where I do the vast majority of my research. And so we're going to talk about 3 very different kind of forests, in that we have ash forests, which are usually wetland kind of forests, or mesic. All of the sites that I used for this study that covers all of the lower peninsula of Michigan, northeast Indiana, and northwest Ohio, all of these forests have some sort of wet, swampy area in them. They're wetland forests. They have these important standing water time periods for the forest. And so we'll talk about as humans, our impacts on the forest and what has happened and what has changed over time in these forests across this large landscape scale kind of study. Then we're going to talk about jack pine forests up in the UP, and this is in Pictured Rocks National Lakeshore on the shore of Lake Superior. And here we'll be looking at the ecosystem level. So we're looking at individual stands of jack pine within a functional system, as opposed to the landscape that we'll look at with the ash. And then we'll talk about sugar maple in Noble County at Gene Stratton Porter State Historic Site. Very different forest, still mesic like our ash, where we have some water, we've got really rich soils, but a very different kind of scale. And here we're going to be looking at the stand level within a big forest, but at this one specific stand, what's happening to the trees and the forest as a unit at that scale. So for dealing with ash, if anywhere in the Midwest and the eastern half of the US, if we talk about ash as a species, we have to talk about emerald ash borer. This is an invasive beetle that was introduced to Detroit area in the mid to late 1990s. We didn't know about it until the early 2000s, though. So there's an 8 to 10 year period where this beetle existed in North America, and we had no idea it even existed here. So it had time to establish and start spreading out from the Detroit metro area into the rest of lower Michigan, into Indiana, Ohio, down into Kentucky and Missouri, and basically the eastern half of the US and Canada now have this beetle in the forests. So when a emerald ash borer EAB larva feeds, it feeds on the phloem, which is the sugar transport system for the tree. And we can see it progresses through time. It goes from really small larvae, it goes through 4 instars, and it gets bigger, and it feeds on this phloem, and it gets bigger and bigger and bigger, and eventually will mature and then emerge as an adult beetle. One larva in the tree doesn't do anything bad. The tree can recover from this. One larva in the tree, it doesn't harm the tree. What really harms the tree is when we have thousands upon thousands of individuals feeding in the phloem, and it severs the phloem and severs that transport system. And so now the tree can't send sugars in the summer, it can't send them down to the roots for storage. In the spring, when they're getting ready to leaf out, it can't pull sugars up from the roots and put those in the leaves. For maturation of those leaves, and eventually the tree starves to death, because as the years progress, as it moves through time, the leaves get smaller and smaller and smaller, and eventually can't sustain itself with really tiny leaves. So this study is something that I started as a postdoc in 2007, and I continued as I did my sabbatical last fall, looking at these 44 sites across the entire study area. So this is a landscape scale kind of study, looking at how did the composition of these forests change over a decade of attack from emerald ash borer, and then what happened to the rest of the forest as ash was lost from those forests. So here's me standing in the forest, measuring trees, and you can see that this is a relatively wet site during the spring, because there are flood lines on the bases of the trees. So you can see there's a few inches of standing water for an extended period of time in these forests. And so this specific site has a lot of silver maple and elms in there, as well as the ash. Not much in the understory of the forest because of the flooding. It's just a repeated disturbance. Again, it has a beginning and an end. It has a boundary around that flooded area. Other things that changed through time in these forests. This was a site in middle part of Lower Peninsula, Michigan, there used to be a road here. When I first did this study, I have a site right through here. I would park on the side of the road and I'd go into the woods and do my survey, but they moved the road all the way to the left of the photo. And so now we've got this completely different system here, and this will start to progress through time, and we'll have trees start to encroach, and it will become connected with all of the other trees there shortly. So it was just kind of a surprise when I pulled up and my site wasn't where I thought it was, and it didn't move, but the road did. So the results of this study are striking. They're not surprising though, because we knew leading up to this that emerald ash borer kills ash trees. We knew that it was going to remove a lot of ash from the forests. We just didn't know how much really is being lost. So in this graph here, I've got 2007 on the top row, and I got 2017 on the bottom row. The left-hand column is live ash, and the right-hand column is dead standing ash. And so what we can see in 2007, there was a lot of live standing ash in these forests. Overall, there was about 26% of the forests were ash. But we get pockets where we have over 40, 50% of the standing trees were different ash species. So what that tells us is that green ash, black ash, and white ash were defining species for these forests. They were defining what was that forest by being defining that three-dimensional space. And in 2007, the amount of dead ash that was standing in these forests was really low, less than 10%, mostly less than 5% in all these forests. So if we look at just the numbers, we have in 2007, we had 26% of the forests were ash just by counts. In 2017, it was 2.5%. So you see this major reduction in the amount of ash in these forests. Dead ash in 2007 was about 1.3%, and then in 2017 it's 20%. So we get this complete inversion of the values in a matter of 10 years, where we have this major defining species being removed, and now we have its dead standing individuals as the defining characteristics of those forests. So overall, I was able to quantify about 84% reduction in the amount of ash in these forests. But if we look at these by states, what we see is that Indiana and Michigan were very similar, but Ohio had almost 100% loss. There's a few sites in these two counties here in northwest Ohio, and these were parks. These are state forest properties. These are properties that should have had some protection, but then all those trees were lost due to emerald ash borer. And those 80% kind of values are a little bit lower than what previous studies had found. The Ohio numbers match those previous studies, but those previous studies were done in Ohio. So there may be something going on with climate and weather and everything related to the forest definitions in those states, or in that state. And we can look at it all different ways, but what we see is that our red line here is live ash basal area, which is kind of a measure of volume of the forest, and our dead ash in the black line, and we see this complete inversion of the amount of standing dead to live trees. And the overall forest basal area, so the volume of the forest, it actually increased a little bit, because now that we have ash being dropped out and the canopy opening up, we have massive growth of other trees coming in, and they get recruited into larger size classes, and then they end up getting measured. So we see this shift in the volume of the forest, even with ash being removed. And with that shift, we have to think about what's happening with the composition of this forest, with this major defining group of species being lost and removed. So we can look at dissimilarity. And oftentimes when we talk about stats, we talk about things in these kind of odd ways, but instead of talking about similarity, we're talking about dissimilarity. How dissimilar are these years at any given site? And so that gives us an idea of how influential is that loss on the composition of the forest. So in our ratio here, the top we have our dissimilarity between 2007 and 2017 at each site. And we're dividing that by, if we take the 2007 data and just delete ash from the data and then calculate dissimilarity, what's going on there? And so a value of 1 would mean that just simply deleting ash was what changed and caused the dissimilarity. Anything greater than 1 could be an indication that it's actually a bigger influence than just being deleted. It's not just being lost that's causing the change. It's something else functionally that's being lost. And so if we look at all the sites, we see several sites do have values below 1 and at 1. And those sites would be that ash being lost from the forest really didn't impact the composition other than just being lost. But the large number of the sites have these values well above 1, which means that they lost ash, they lost this defining functional group of species, and that completely changed the composition of the forest. And so what I found were that there were shifts to some of the maples, red maple, silver maple, sugar maple, which would make sense in a well-drained mesic site, so a site that has good drainage and has really rich soils, which these do. They're only ephemeral wetlands. They're not constantly swamped. So this makes sense for the area that I was studying. Well, I also found black cherry, quaking aspen, and balsam fir coming in to some of these sites, which are starting to get to those drier sites. And so we can see a change in hydrology that's happening, potentially allowing for the establishment and dominance of some other trees. But interestingly, at 10 of my sites, the dominant standing tree were dead black ash and dead green ash. So they were making up defining the volume of the forest. And so by having these dead standing trees, we're going to progress to something else dominating, something else living dominating it. But it shows the importance of these trees in terms of composition, that they're dominating. They're dead individuals that are standing in the forest are what are dominating the volume of the forest. So some of my sites had quite a bit of ash regeneration, and regeneration is just the establishment of seedlings coming up from seed. They're going to be the cohort of trees that will move up into the forest. So at some of my sites, there are these carpets of ash seedlings, but other sites like that first one that I showed where I was standing in the wetland, there's very little or no understory ash coming in. So if there's no seed coming in, there's no trees coming back. So the big things to take away from this is that these forests in the Great Lakes are changing substantially due to the loss of ash. Those ash species, green, white, and black, were very, very important. They were stand-defining species that basically define that three-dimensional space. And now, looking into the future, seeing where these forests are going, ash is going to be a small component of the forest. It's not going to be as a key group of species that we once saw. And that's due to the loss as those trees are attacked by emerald ash borer. And so those places that we do have ash, they're isolated, they're patches, they're not connected like they used to be. And so that's a devastating loss for the region. And what that does is it changes the successional pathway. It changes the trajectory of that forest through time. So where that forest was traveling as a time machine forward is changed, and now it's veered off and going a different direction because of those trees being lost. And that also then impacts the resiliency of that forest. So a forest as a functional system, when a disturbance does hit, they have the ability to respond. They can bend and flex as a group and recover after a disturbance. As you start losing key species, that resiliency is lost, and we start losing that ability to respond quickly to disturbance, and could potentially mean the loss of the forest as a unit. So that's ash. Little depressing because we've got all these trees being lost, and we have this complete removal of groups of species from the forest. The next one is a very different forest system, dealing with jack pine within sand dunes. So this study is in Pictured Rocks National Lakeshore, which is along Lake Superior. And jack pine as a species is fire adapted. That means that if there's a fire that moves through a jack pine forest, it regenerates, more seed germinates, and the understory comes up with trees very quickly. But it's not a requirement of jack pine. It can colonize and grow without fire. And so that's what we see here is we have a ecosystem that does not have fire as a disturbance, but we still have lots of jack pine. So that makes it a kind of a unique forest for jack pine in that there is no fire. And again, this is in Pictured Rocks National Lakeshore, which does not have fire in the sand dunes. And these jack pine forests are important because they're cover for wildlife. They provide habitat for some orchids because they are the only shade within the sand dunes. So lady slippers, there's some ram's head lady slipper, which just couldn't get a good photo of. There's some other orchids that use these forests. And so the Park Service was interested in understanding what's going on with the jack pine so they know how to manage the orchid populations that exist in the dunes. So this is Lake Superior up here. We've got our site in Pictured Rocks. This is the Grand Sable Dunes. This dune field is rather large. It's about 6.5 kilometers long, walking from one to another. So now, instead of being the landscape scale that we saw with the ash forest, we're looking at ecosystem scale in this dune field. And so using transects, me and a grad student and a former grad student surveyed these forests running perpendicular to the side edge of the dunes out towards Lake Superior and 1.5 kilometer transects. And we just measured every jack pine we encountered along this transect. So if we go back here a second, this little bowl that's formed right here has jack pine along the sides and jack pine along the sides here. You can see these kind of light green areas. Those are places where there's hardwoods and some other deciduous trees are actually making the forest. And these darker greens are the jack pine. And so this bowl here and this little corner here, this is a blowout that's formed on this big ridge that you can see from anywhere in the dune field. So that became our frame of reference where we were at when we were navigating. And so if we look at, this is that bowl, jack pine coming all the way around. That's that little blowout that we could see from anywhere in the dunes as our frame of reference. And what we see then as we turn to the right, there's mature jack pine in the background. There's some immatures here in the foreground. And then we have these really little ones out here that are basically bringing the jack pine forest out into the dunes. They're colonizing, they're spreading, they're establishing as a new forest as it moves out into the dune area. And then there's little jack pines that look like that. They're just isolated by themselves. Seeds got there and they established and started growing. Since the focus of this study was on the jack pine, we oriented our transects so that we always went through the jack pine forest, but we went through some other areas where things like balsam fir and sugar maple and paper birch were a little bit more dominant, but across this ecosystem that we were focusing on, jack pine was the dominant species. So jack pine here, the basal area again is just kind of a measure of volume of the forest that's made up by that species. So even without fire, jack pine is the dominant species in this forest system. Of the over 1,300 individuals we measured, about a third of them were less than 30 centimeters tall. So we're measuring height for up to 30 centimeters, and then above 30 centimeters, we were measuring the root collar diameter, so the diameter of the tree itself. So these are going to be trees like this, that are relatively short. So these are a few years old. They're establishing as this kind of new cohort of seedlings for the forest. And the nice thing about these, this 34% of those trees, it's pretty evenly distributed. So we get some even distribution of seed germination each year. New individuals, so the really short ones are coming in, and we get some taller ones. So we get these progressions of ages throughout all of the individuals that we measured. And then above 30 centimeters, we measure the root collar diameter. And you can see that that's skewed to the right, and we have then lots of these really small, relatively small jack pine that are 5 centimeters at root collar. So this is the 5 centimeters at the soil surface on the stem of the tree. But those trees could be anywhere 10 feet tall or so. So we could have variable heights in there, but we have these kind of smaller trees that aren't quite mature that are dominating. And the big trees down here that are the mature trees producing seed, there's fewer and fewer of them, but they're still there. They're still part of the forest producing seed. When we line up basal area and the number of offspring, the number of seedlings below 30 centimeters, we don't see an exact match of where things are occurring. Because the red lines are basal area, the black bars are regeneration, so the number of seedlings. we don't see this lining up in any way, shape, or form. We get variable heights on the red lines, variable bars, all the way through, except for this third transect, where there seems to be a clear pattern of, as there's more basal area, there's more seedlings of jack pine. So it's kind of an interesting relationship that doesn't exactly line up, but it gives us some idea of where this jack pine is growing. But if we look at it as an ecosystem as a whole and relate basal area to regeneration, we do see a positive line that as there's more jack pine, we're going to get more jack pine. And if we look at the other species that aren't jack pine in the forest, as those increase in dominance in basal area, we get less jack pine, which makes sense. But the nice thing about this is that we're getting the continuation of jack pine, even though we don't have the normal disturbance that would be bringing jack pine in. We don't have fire. Just looking at the forests here, so you can see this is the transect line. Each dot is a location of where we measured individual trees along that transect. And you can see some of these have very clear patterns where we've got this long line here of open forest, and we got some green, lighter green here because this is not jack pine forest here, and so it ends up being a gap in seedlings. We got this big bowl that forms. It's completely bare of vegetation, and so we don't find jack pine across that bowl. This transect had some interesting patterns where we had lots of little seedlings trying to fill in this open gap. So over the last few years, we can think back in history, this would have been a bowl that was created during a winter storm. We've got a storm coming in off of Lake Superior, blows in, basically cuts this bowl, and now we've got jack pine pollinating, and over the last few years, 10 years or so, this has started to fill in, and we can see seedlings coming in along those bowls that are stabilizing. And so if we look at height, again, we're looking at this as using some interpolation to basically make a solid map, and then looking at just the contours. Height is for our seedlings less than 30 centimeters. We find some areas where we get some taller trees, closer to 30 centimeters, but in these areas where there's slow regeneration, slow colonization, we get lots and lots of tiny trees. Trees that are anywhere from 5 to 10 centimeters tall, so really, really short trees, all trying to colonize these areas that are basically new. And if we look at root collar diameter, again, our bright colors are going to be our bigger trees. So we get pockets where we have really big trees. But again, this transect here that goes through this really odd kind of pattern, these are all really short trees that have, and then the trees that are over top of them are all really small as well on that low end of the root collar diameter. Get a couple of larger trees along the way, but this pattern of colonization kind of has these smaller individuals. So even without fire in these dunes, we have jack pine regenerating, which is great for maintaining a jack pine forest, allows those mature trees to eventually die, and allows jack pine to keep basically sustaining itself as the forest in these dunes, even without fire. So fire is usually a major component of a jack pine forest. So seedlings are establishing. We still have mature trees that are producing seed. And the interesting thing with jack pine is that an old growth jack pine forest is 80 years old. So we can get to an old growth jack pine forest here in a very short period of time, but this isn't there yet. And those jack pine stands are really important for wildlife, for some rare plants, and understanding what's happening in the dunes. Usually when jack pine doesn't have fire and gets to old age, it gets attacked by jack pine budworm, which is just an insect that's native, that's going to attack these old trees as it gets to 80, 90 years old. But we didn't find much of that. We actually found very little occurrence of jack pine budworm in the dunes, which means that this forest isn't quite to that old growth kind of stage. It's still a little bit young as a forest. So we're going to still have sand movement. We're going to have disturbance. We're going to have excavation by storms. We're going to have accretion by storms. One of my favorite places in the dunes is this area. When I was doing my master's up there, I keep going back because it's my favorite place in the world. But there's a spot where a storm came in and dumped a massive new dune and made this big blowout over the winter. And in June, I could dig down a foot and find ice and snow buried in the sand because as that storm just brought so much sand in, it insulated that snow and ice. So we're going to always have those. They're always going to be disturbing these jack pine forests, but it looks like jack pine is going to keep colonizing those new areas and keep sustaining itself as a forest. We will see some encroachment from balsam fir, from sugar maple and paper birch on that south end of the dunes moving in, but it's not going to take over. Jack pine's going to stay there. It's going to be able to sustain itself. So where our ash forests have this major diversion from their successional trajectory, their pathway because of humans, here we're not interfering with the jack pine, and it's actually moving in the future towards its intended path as a forest. So the last one is looking at sugar maple. Again, very different kind of forest type than the other two. And we're looking at a stand in Noble County. So a stand is just a unit of the forest where we have a group of trees that are all kind of related functionally and kind of define this grouping within the forest. It's not any set size. It can be variable in size, just like a forest as a unit can be variable in size. But we're just looking at one stand. And this is at Gene Stratton Porter State Historic Site, just outside of Rome City. And so Gene Stratton Porter was an author. She acquired the property east of the road in the 1920s. And so when she acquired that, she protected that section of what now is the historic site. To the west of the road, there was another private landowner that had purchased it in 1888. We have records of that purchase. We don't know what they did to the property for sure, but there was some protection to that property. Because of the fact that we have aerial photos from the 30s that show it was a closed canopy forest. And so for it to be a closed canopy forest in the 30s, there had to have been some protection decades before that allowed it to actually move through time to become that kind of forest. So we have aerial photos from the 1930s that show a clear forest existed there. So this is a relatively small area. It's only 7.5 hectares, which isn't very big, but it's a stand within this forest. So this is the pink outline. That's the Gene Stratton Porter Historic Site. This is the section that Gene purchased in the 1920s and protected that area. And then it was donated to the state in the 1940s and became the historic site. This is the section that we're going to focus on, and this was owned by a different landowner. I'm not exactly sure when the state acquired this part of the property, but like I said, we can see aerial photos from the 40s that was forested at that point in time. But by looking at the forest in several different ways and using interpolation to kind of fill in the space between the survey plots, we can get an idea of what's going on in this stand that's part of the property. And if I go back real quick. So the reason I'm calling this a stand is because we're just looking at this block, and there's forest down here that these trees are interacting with pollen. There's trees here that they're interacting with. There's trees all the way down the road going towards, going south. That are part of this continuous forest, and we're just dealing with this one little block here. But looking at canopy cover, it's a closed canopy forest. 95% canopy cover across the entire forest, and as the trees grow up into the canopy, they start growing together. There are some things of crown shyness, which is basically where there's a line between the crowns sometimes happening, but we have a closed canopy forest, and for it to be this way, it has to be allowed to progress on its own for a long period of time. We do see some patches, so on this interpolation, the light colors are the higher values and the dark colors are the low values, but the low value in this is only 92%, so it's still a closed canopy forest. Diversity across the forest is kind of patchy, but it makes sense because down here where we got low diversity, that's also the area we had low canopy cover, so there are just fewer trees. There's a creek that runs through the property here, and that's probably where that plot ended up, was right near the creek, so there's just fewer trees that are making up the canopy and the diversity there. Some other things that can give us ideas of past land use are things like litter depth and soil compaction. And you can see litter depth here and soil compaction kind of mirror each other, and that the highest compaction is over in this left-hand, southeastern corner. and then litter depth is also the shallowest there. And so that gives us an idea that there's possibly something going on with past land use, farmer using it as a turnaround for a tractor or anything like that. So we get some compaction there in the forest. Mid-story was really sparse. You could stand in the forest and look straight across and actually see almost through the entire forest because there was nothing in that layer of the forest. It was just bare. The only place that we did find sugar maple as a mid-story species was in this really high canopy cover area there on the north end, which makes sense because sugar maple regeneration happens underneath a dense canopy of sugar maple over top. And the mid-story was really sparse too. We only found 20 species the understory, 20 species of understory species, and half of those only occurred in one location at one point. So just looking across the forest, there was this lack of consistent species across the entire forest, which both mid-story and understory, they make sense for Indiana in a kind of middle-aged forest. It's not old growth, it's not regeneration, new growth forest. It's kind of this middle-aged forest that's been protected for 90 to 100 years. So it makes sense. This matches almost all of sugar maple forests in Indiana. Something else that we looked at was coarse woody debris, which as a tree falls down and becomes a log in the forest, that becomes what we call coarse woody debris. As it starts to decompose, it's releasing things into the soil, but it's also important wildlife habitat. It's important for regeneration of plants and trees, and it accumulates as the forest ages. So we see this accumulation of coarse woody debris as a forest progresses through time. And so in the coarse woody debris interpolation, we see a high value here. Again, this is where that creek is, and that plot would have had low coarse woody debris just because we had fewer trees in that area. And so the interesting thing is there are models that exist using coarse woody debris and age relationships to try and understand the accumulation of coarse woody debris. And so we ended up calculating about 28 meters cubed per hectare of coarse woody debris in the forest, which crosses the line in two places. So this line here is somewhere in the 50-year-old age of the forest, but we know that this forest existed well into the 30s, so it's not only 50 years old. So we know that much, that intersection of the curve is not correct. What it probably is this line here where the forest models out to being about 91 years old. So again, that kind of strengthens that idea that between 1888 and 1920s, there was some harvesting going on. The owner was taking trees out, using them, so there was some activity in there was some disturbance. And after the 1920s, when Gene Stratton Porter has bought that other property and then it gets added to the historic site in the mid-1900s, we've got protection there. So it makes sense that this forest kind of aligns with a 91-year-old sugar maple forest, which is not old growth. Like I said, old growth in jack pine was 80 years old. This is kind of a mid-aged sugar maple forest. So this is, again, this is Gene Stratton Porter State Historic Site. The reason I did this survey with a couple students was that the land manager at Gene Stratton Porter is associated with the State Museum and isn't a forester, doesn't have land management background. So he asked for some assistance there, trying to understand what's going on in the forest. What do they need to do to actually maintain this and protect it? So basically, it's had some protection before it was a historic site, and now it has even more protection as part of the historic site. And it matches what we see in a lot of sugar maple forests in northeastern Indiana. The problem with Indiana is that most of our forests are relegated to these little patches, little pockets of forest. You drive north into DeKalb County, south into Wells and Adams counties, you see agriculture with little pockets of woodlots dotting the landscape, and those are the forests we have left. There are some larger pockets, some state parks, some nonprofits like Acres that have these larger properties, but those are still very small remnants of what was the forest in Indiana. So basically, every forest in our region has been manipulated by humans in some way, shape, or form. Even if you think it's a wholly protected, there's very few places that haven't had human touch and manipulation. So we need to understand what's happening in those forests. We need to know, at Gene Stratton Porter, we've got this middle-aged sugar maple forest. It's been manipulated, it's been changed, but what's it going to turn into? What's it going to progress to? What's its future as a forest 10 years from now, 50 years from now, in terms of the composition and structure? So again, it's going to progress. It's always changing. So this sugar maple forest is going to progress through time, but it'll probably stay sugar maple, but we'll start seeing beech come in. We'll start seeing some later successional kind of species come in as it progresses through time. It's going to stay close canopy. There's going to be more and more coarse-woody debris accumulating, which is really important for wildlife and the function of the forest. So overall conclusions, forests are not stagnant. They're always changing through time. Like I said, it's a time machine moving forward. And we can get an idea of what it was in the past and where we're at right now, and we can predict where it's going to head to in the future. And so those changes are influenced by disturbance, but we as humans are a major source of that interference. We're the source of the change that happens in these forests oftentimes. So if we look at the landscape scale with the ash mortality and survival, this was an extremely rapid change. 10 years of change is very short for the forest. And so for those defining species to be lost, it happened in a snap of the fingers, and time just progressed very quickly for those forests. So it lost its inherent resiliency. It's diverged the successional trajectory. It's going to be other forests that we couldn't have predicted 20 years ago because of this loss. Jack pine, again, without that kind of human interference, we're seeing this regeneration happening. We have disturbance coming in, but it's not influenced by humans. And so we've got this response of a forest to the sand movement in the dunes without fire and still maintaining itself. So it's going to maintain itself. We're going to get some encroachment from sugar maple and from paper birch, and then also some other conifers like balsam fir, but it's going to be really, really slow because we always have that movement of sand that's kind of limiting their encroachment. And then the sugar maple at the very localized scale of a stand, it's had some interference from humans, but we get this kind of progression, this aging on its own through time. And so it's going to remain sugar maple. It'll eventually reach kind of an old growth status with some beech in there and sugar maple, but that's going to be decades from now because we're still in this kind of mid-aged sugar maple forest that had some protection and it's had some movement through time. So at all these different scales, the forests are changing. At all these different scales, humans have had some sort of interference with the forest and caused some change, especially when we're looking at the landscape level for ash or the localized level for sugar maple. But even with our interference, these forests are going to recover into something else. So even though we've removed all of the ash from these ash forests, they're going to recover into something else. They're going to recover into maple or black cherry or something else that's going to be the dominant species. It's going to take time. It's going to need some time to move into those types of forests, but it'll happen. So I've got acknowledgements. I've had collaborators and students work on all these projects. So the ash mortality survival, I've had collaborators at Michigan Tech and the USDA APHIS over multiple years. The jack pine study, one of my grad students from here at Fort Wayne and a former grad student who's a biology teacher at Snyder assisted on that one. And then the sugar maple forest, I had a couple students, one from IU and a student from here in Fort Wayne. So students involved and also collaborators looking at these big, large scale kind of projects. So with that, I think there's time for questions.
Give him a round of applause first, though. Thank you very much, Jordan.
Yeah.
We do have time for questions. Are there some questions for Jordan? Especially students who might want to turn the tables on him finally after all this time. Take-home tests sort of thing.
Not a student.
Yeah.
So you said the Park Service was interested in the orchid. What's the relationship between the jack pine and the orchid, and what did your study do for the Forest Service in that respect?
So the reason the orchids use those areas is because they provide, the jack pine provides shade. In the sand dunes, jack pine's really the only forest, except on the south end where the hardwoods are starting to move in. And so those sandy soils are well drained. They're very thin soil crusts, and the orchids like that shade. They like having that lower amount of light coming in. So what this is going to do for the Park Service is it gives them an understanding of what the jack pine is doing. Because they hadn't done surveys and hadn't been able to quantify how is it progressing through ages, how is it changing over time. So this gives a starting point to know, okay, well, we have mature jack pine, we have regeneration happening both in the areas where we have mature jack pine, but also in the areas that are open bare areas right now. So we know then that there's going to be jack pine forest, and the orchids will just kind of move and follow with the jack pine. So the seeds will disperse into those new areas and still exist as part of the forest in those new jack pine forest stands that come up within the forest.
Actually, I'd like to ask, I'm sorry, I'm going to throw my own question in first, and we'll get to you. You noted that Indiana and Michigan have not had as much death of the ash. Ohio is what you would expect in the high 90s. You mentioned you thought it was maybe Ohio. Was there something maybe unique to Indiana and Michigan that made that happen?
I don't know exactly why there was a relatively low mortality in some of those areas. As you move further north, emerald ash borer takes a little longer to mature, and so there may have been population density differences. Even though it was introduced to Detroit area, those northern parts of the state kind of have climate that would slow down and maybe limit how dense the emerald ash borer populations can get. One of my other studies that I've done in the past looking at longitudinal gradients and going down through Kentucky and Missouri and up through Michigan. In the south we get bigger beetles and they lay more eggs compared to the north, and some other studies have shown that they take longer to develop up north. So there could be a whole range of climate there that's kind of interacting. Indiana, I think the reason it's a lower loss there, even though we're at the same kind of line as those Ohio counties, that's probably related to just the density of ash in those sites. So they inherently were at a lower density just because of the type of forests they were. And so they may have lost large numbers, but they didn't have the trees originally for emerald ash borer to take advantage of. So it could be part of those two.
Okay, thank you. Another question?
So is anything known about how emerald ash borer is specific to ash? Does it go to any other species?
The only crossover that's really been shown is in a fringe tree, which is native to southeast, and it's the same family as ash, and that one is definitely a lower success rate of the beetle on the tree, but it still can go through all its stages and emerge as an adult. I'm sure it has something to do with the chemistry of the phloem, the growth of the tree, its soils that it's growing in. I'm sure there's something to do with the mycorrhizal fungi that are available, interactions with any of the bacteria in the soil. I threw in bacteria because I know that's an important part. All of those things kind of relate, and it only is detrimental. It only kills healthy North American ash. So in China, Japan, Korean Peninsula, the native ash there is attacked, and the beetle can emerge, but nowhere near at the numbers that we get here in North America. So there's something to do with the way the tree is responding in terms of damage, in terms of its growth and the chemicals within the phloem. That's all kind of playing into the defenses of the tree that it can't deal with the fact that emerald ash borer is attacking it. So so there is something specific there that they're feeding on, that if you put the beetle on, any other tree, it's not successful because those other trees have defenses that.
Okay, so, and also then for the size of the tree, is there a limit to the size of the tree for the infection?
Basically down to 2.5 centimeters in diameter at any point on the tree. So you could have a mature tree and every branch down to 2.5 centimeters is going to be attacked. You could have a sapling that is, or a street tree or something in a development where they plant a whip and you get to 2.5 centimeters in diameter and it gets attacked. So it's basically, once it gets to that size, there's enough phloem for the larvae to develop in, and so then the beetle feeds on it, larva develops and emerges.
I want to thank Jordan for giving a talk in the series, the College TV Speaker Series this year. I want to thank the sponsors who are, of course, College TV, as well as the PFW Institute for Research, Scholarship, and Creative Endeavor, as well as the Professional Development Subcommittee here at PFW. Thank you very much. Please be sure to look for other opportunities. Come out and hear faculty talk about their work. Thank you very much.